All right, let's start. So, are there any questions before we begin? Anything you want to ask? Okay. So last time, you're looking at the interfaces between semiconductors with metals and other semiconductors. And we have seen that you're looking at the edge of our band, and this is more or less the real space. So this is my conduction band, valence band, and we have seen that if you add impurities that donates electrons into the system, you shift the Fermi level slightly higher, and its net result is to create more electrons in the conduction band. Okay, and the opposite case was doping with acceptor states, acceptor materials or elements, and this was basically this gives more holes into the system, so it contributes to hole conductivity. So this is p-type doping, and this is n-type doping. And if you remember, Fermi level would lie in between in the intrinsic case.
So only in the doping case, it will be shifting of Fermi level.
Yes.
So when we do n-type doping, there will be more electrons in the conduction band.
Exactly.
So other case, more holes because acceptance.
Yes. So, and the net result, I mean, if you remember how we derived the Fermi level, it comes from counting of electrons, right? So we started filling up a potential well with electrons of spin 1/2, and then we define the Fermi level to be the highest occupied energy level. And if you remove electrons from the system, it's of course expected that you lower the Fermi level. Or if you add electrons to the system, it's quite expected that you add electrons into the system. And its net result is basically creating electrons in the conduction band or holes in the valence band. And then we looked at their junctions with metals. So you can take a semiconductor and a metal. And if you remember, there were two important quantities, or parameters, I should say. This is my vacuum level, so this is 0 electron volts. And this difference was defined to be the work function of a metal, which is the top of the Fermi level for metal. So this is the metal side. This is the semiconductor side. And also we had another definition, electron affinity, which was defined from the conduction band of a semiconductor. And their relative positions or relative magnitudes matter a lot when you bring a semiconductor in junction with a metal, because let's take a look at this case where you have an n-doped semiconductor making a junction with a metal. So in this case, I'm going to have my Fermi level to be here for the semiconductor and Fermi level for the metal to be here. When I bring these two together, when they make a junction, the energy throughout the system must be uniform, at least for the bulk, because if you have extremums or minimums and maximums, if you like, within the material, then all the electrons will try to rush there, and then quickly that state will no longer be an extremum. So everything will be leveled. Now, when we bring these together, we have seen that the first effect is that we start inducing surface states, because the electrons in the semiconductor now can leak, if you like, into the metal. Their wave functions can leak into the metal, and this creates extra states. And as we have seen, for now, we are not interested in the surface-induced, metal-induced states at the surface, because the depth of such states are extremely, extremely shallow. So we are more interested in a range of a couple of nanometers rather than a nanometer or so. So when we look at that, we will ignore it for the moment. So what will happen when I bring the metal and the semiconductor together? So something we call band bending will happen, okay? So because now my Fermi level lies here, and it tries to match the Fermi level of the metal, okay? So if you like, we create something like this, okay? Because now I accumulated charges here as some of the electrons left this region and ended up being in the metal, because my electrons have higher energy compared to the metal. It could be the other way around, by the way. It doesn't have to be this way. It all depends on the work function of the metal and electron affinity. So for that reason, choice of metal is extremely important when you want to make a device out of semiconductors. You may end up with a junction like this, and if you consider this junction, let's say I send an electron from the semiconductor side to the metal side. There is an energy barrier that this electron has to overcome. Okay, so this barrier has to be, the energy of this barrier has to be provided to the electron so that it can overcome and go to the other side. So when you have such a contact, we call them Schottky contacts. And it's a highly resistive contact. So it's not an ideal contact. But there are cases where it becomes extremely useful when we make devices like diodes. We want to have Schottky contacts because it's a rectifying contact. It allows electrons passage in a single direction. Okay? In another case, we can have, for instance, let's say this is my conduction band again. This is my N-type material. And now I have a metal. Oops, it's dying. I have a metal that has a smaller work function. So the Fermi level of this guy is slightly higher than this one. So what will happen in this case? Well, again, I'll have a band bending. So this band, but this energy band will bend towards down, okay? So my Fermi level, okay, now of course, will be equal to the Fermi level of the metal. But now, if I send an electron from here, there are empty states that my electrons can fill at this gap. And when I send electrons from this side, there's no barrier that electrons will see. So in this case, I form an ohmic contact. And this is the type of the contacts that you want to make, especially if you want to probe your material. Okay? So these two types of contacts are extremely important in the study of semiconductor metal junctions or semiconductor junctions, because you can have, for instance, two semiconductors, one n-doped, the other p-doped, and when you bring these two together, again there will be a band bending to level the Fermi levels, and as we have discussed in the previous lecture, a Schottky barrier between these two will form. Okay. So, any questions regarding these? I mean, I'm going rather fast on these because, again, you should be doing your own research to figure out, or ask questions to me to figure out what's going on here. But these are basic stuff in condensed matter physics or any materials study. Any questions? Mm-hmm. Mm-hmm. Well, it's well, it depends. It depends heavily on the electron affinities of the materials that you have. You can, in principle, make an ohmic contact between two semiconducting materials. That is, one is n-doped, the other is p-doped. If you can have a very bizarre configuration, like in one case you can have a small band gap of one type, and I don't know, I'm not sure about this, but a larger band gap, and also the electron affinity of this guy is shifted so high that there will be no band bending, and you can easily send electrons from one side to the other. So the formation of a Schottky barrier heavily depends on these two and how these bands are aligned with respect to each other. Does that answer your question? No? Well, let's try again. Could you elaborate your question a little bit more so that I can?
I want to know, for example, how we can specify, define what each one is Schottky, each one is ohmic.
Oh, well, if you're talking about how I can specify by looking at it, all you have to do is look at what will happen when an electron approaches to the junction. If there's a barrier, energy barrier, like in this case, a Schottky barrier, so this is called a Schottky barrier. If you see a barrier, then it's most likely a Schottky contact. Not always, because you can have a very shallow barrier, like, that's a possibility, and even a tiniest bias that you'll apply will give these electrons enough energy to overcome this barrier. Okay, so it requires special attention. I mean, you need to study the basically the energetics of how these barriers form.
So, for example, that it's both would be a Schottky contact and ohmic contact. If we change the direction of the electric
Well,
charge.
okay, now what you're talking about is in the diodic behavior. This is what we get, right? So towards one side, this is an IV curve. When you apply voltage, well, let's say positive voltage, then you get a current flow through the barrier, and when you apply negative voltage, you don't get a current through the barrier, because now you have to provide quite a lot of energy to the electrons so that they can travel. Now, in this case, again, this part requires a special attention as well, because the transport back through the barrier is also an interesting case. And at sufficiently high potentials, you enter into an ohmic regime. So there's a linear relation between voltage and current, so you can define a global resistance. But as the potential you apply becomes lower and lower, then there's an exponential regime where electrons at least have to gain enough energy so that they can pass backwards. So it's, again, there's no straightforward answer to that question as well. It requires you to study exactly how that IV characteristics works. But there's a general formula that you can write down for an IV characteristic of a Schottky contact. Okay. Any other questions? Yes, please.
In this session, when you stated that if you put an empty semiconductors close to each
Mhm.
other, but we understood that this electric field has the reason that
Mhm,
there
mhm,
is
mhm,
also
mhm.
forces. And in those semiconductor and metal, we also see this barrier, but
Mhm.
it's the same idea or
Okay, well now, I think we can say it's a similar idea, because again, to be able to form this barrier, we begin with a configuration like this, where we had more energetic electrons compared to the metal. So these electrons will try to fill up the states that are available here. So which means eventually you're going to leave abundance of positive charges at the interface. And those positive charges will create their own electric field, which will result in a potential step. So I think we can say the idea is very similar. I mean, if you look at it in a physical perspective, that's pretty much what's going on. But once you get used to the idea of these energies and looking at how the electron would move within these energy barriers, then it becomes relatively straightforward to look at these junctions. Now, next thing I would like to do is something like this. Let's say I have a p-type semiconductor, and then I embed n-type semiconductors into this p-doped semiconducting material. So, I mean, it's straightforward to see now that I'll form depletion zones here and here. So it's like I have two diodes, if you consider this and this and this and this connected. Now, there's another thing that I'd like to do. I'll add an insulator here. Okay. And then on top of that, I'll add a metal. And the reason why I do this is I would like to modify the energy of this barrier by applying an electric field, an external electric field. So if you consider this, let's say I apply a positive voltage to the metal. What will happen to the electrons here in the p-type region? Okay, does everyone agree with that? So I have electrons. Of course, within even I have, or you can consider that I have lots of holes more than electrons. So when I apply this positive voltage here, then I'll attract electrons. Another way to look at it, I'll repel holes away from here. Now what happened? Let me get rid of these holes. Now I attracted a lot of electrons to this interface. But now if you consider our initial idea, we would form, I had these positively charged ion cores and negatively charged ion cores. And the problem here was holes wouldn't be able to overcome this potential barrier due to these positively charged particles. But now I have excess electrons, which modifies that potential barrier itself. So at sufficiently high voltage, this depletion zone thins out and basically it becomes zero for both sides. So what happened here? Now I formed a channel from this side to the other side that's made up of electrons. That makes sense, right? I applied a voltage, I attracted all the electrons, I repelled all the holes away. So I basically removed the condition that we talked about when we bring an N-type and P-type material. So we will have positive charges on the one side and negative charges on the other side. There will be a built-in electric field, and that electric field formed a barrier like this, which prevented electrons and holes to go from one side to the other. And by attracting enough electrons, basically I modified that barrier, so now I have a channel from one side to the other. Now this channel, typically we call source and drain. Basically by tuning this voltage, I can control the electric flow from source to drain. So this device is called transistor, and specifically it's a MOSFET, which the name comes from. We have a metal, we have an oxide, this guy, which acts as an insulator, then silicon historically, but you can take it as a semiconductor. Then FET stands for field effect. So it's field effect because basically by applying a voltage here, I create an electric field within my material. And that electric field controls this whole transistor. You can make other types of transistors, like there's bipolar junction transistor, where you have 3 stacks of, yeah. Well, there are 2 good reasons. One, if you place metal directly on top of here, there will be a current flow from metal to the body of the transistor. So it will drain quite a lot of power or current from the gate contact as well. The idea in a transistor is to control the flow of electric current with minimal energy required. There's actually now, I was just going to explain, you can make it that way as well. So you have an NPN type of junction, and you connect one terminal directly to the P side, and then the naming is slightly different for historical reasons. So this is called the collector, this is the emitter, and this is the base. Okay, but their function, oh, by the way, this is the gate. but their functions are very similar. Now, in this case, again, I have these depletion zones. I'm just giving this for general information. We'll not use this guy, but we'll use this one a lot because there is, and you can, if you create a, if you fabricate this carefully, you can create a 2D electron gas in a MOSFET. So these electrons here can be a two-dimensional electron gas, which we have studied earlier, and we'll come back to this. But this is just just for your general information. Now, typically, this one of the depletion zones here is larger than the other because one side has more dopants in it. Now, what you do is you want to send current from collector to the emitter, and by basically adjusting the voltage on the base with respect to the emitter, so you apply a certain voltage, what you do is, again, you reduce these depletion zones, okay? So you now start injecting electrons into this site. Now you have excess electrons that can easily go through here. And other function of these electrons is to reduce the barrier on this side. So above a certain threshold, the current that you'll have is going to be current from collector to the emitter, as well as current from base to emitter. But typically, the ratio of current to emitter to base to emitter is like on the order of hundreds. So you can control the electron flow in such a structure with small amounts of current. So, I mean, you can easily now see, I guess, why these guys are important in modern electronics, because they are amplifiers. If you put a signal from the gate, the current from source to drain will follow that signal. And with such an amplification, like 100, if you can cascade multiple transistors together, so you can have lots of gains. So audio amplifiers, this microphone, uses transistors so that it can amplify my voice to a level that it can filter and do some processing and put it back to you as a clean signal. So these are extremely important devices for modern electronics. And MOSFETs, they're used in cell phones, computers, projectors, pretty much everywhere that you need to process digital information, because when you start putting these devices together in clever arrangements, especially there's another trick that you can add. You can make this N-type and these P-type. Then you switch the whole story reverse. When you apply zero bias, the transistor is on because you have diodes pointing in the opposite direction. The current flow is on. When you apply voltage, you turn off the transistor. So that thing, when you have P-type and N-type transistors used together, is called CMOS. Probably you have heard CMOS before. CMOS cameras, CMOS camera sensors. Have you heard? And these computers use CMOS logic. It's basically using P-type and N-type transistors together, which reduces the number of transistors that you need to use for logic gates significantly. Okay? So that's one device that we can use. And again, we'll come back to the properties of these electrons here, which is a two-dimensional electron gas. And if you look at this book, you will see that most of the stuff in this book, not most of it, but a great majority of the systems that have been studied are essentially 2D electron gases within MOSFET systems. So they are not only important for modern electronics, but also future of modern electronics, I can say. Any questions?
We can just shift the position of the
No, no, no. Not shift, replace. So in the case of N-type, this is what you have. Oops. Sorry, these are P's. So rather than N-type doping here, you have P-type doping.
Okay.
Okay, any other questions?
When we have voltages, so our resistor will go back to its off position.
Off state, yes. Now, finally, we are at the position to start our study of mesoscopic phenomena. It was a long, long introduction to the subject. Now let's go back to this very first lecture. And now give a more rigorous introduction to what are the important parameters are. Of course, I'm going to have to introduce new concepts as I go along, but now let's look at the relevant parameters. If you remember, we defined a bunch of parameters like Fermi energy, and we defined Fermi velocity in our previous lectures. Basically, it was the Fermi energy was the energy of the electrons at the surface of a Fermi sphere. And if you ask what that was, let's take a look at this two-dimensional phase space. Then when we look at the behavior of the electron gas, we would end up with a two-dimensional, like a disk that contains of course, the center of this is at the center of the circle, but you got the idea, I guess. So each of the states corresponds to a different energy value for each K value we have. And this vector that points to the surface was my Kf, that Fermi vector. And now you should be able to at least say, okay, then the Fermi wavelength must be 2 pi over Kf. So it is the wavelength of the electrons that are at the surface of this Fermi sphere. Okay? Wavelength. So if you like, it's the de Broglie wavelength of the electrons at the Fermi energy. Okay, so the Fermi energy is defined by the energy of the electrons at the surface of the Fermi sphere. Now, why is this an important parameter? Because it's the de Broglie wavelength of the electrons, and it will define the quantumness of my electrons. And this wavelength should be compared to several quantities within a material, like the scattering length, so the average mean free path of electrons before they can scatter. Perhaps you can say the lattice constant of the material you have, and so on. So we'll discuss them later in detail, but that's one important quantity. So we can write down, actually we are in a position to write down this lambda f in a more definitive form for an electron gas, so, or if you like, a Fermi gas. Okay. So in 3 dimensions, this is what we have. Pi over 3n 1/3. And then for 2 dimensions, lambda f would be square root of 2 pi over n. Then for 1 dimensions, lambda f is 4 over n. And here n is the density of electrons. Okay. But I would like to do more than just doing some calculations. I would like to be able to measure what this Fermi wavelength is. And it turns out that it's not too difficult, because this is density of electrons. It's something that I can easily measure. And now I'll open a parenthesis and explain how we can measure the density of electrons. Any educated guesses? How do you measure density of electrons in a material? Oh, no, but that would be a calculation. I'm talking about really connecting probes and doing a real measurement. Well, never mind. You'll hear this a lot. Hall effect. What is Hall effect? Is there anyone who hasn't heard Hall effect? Anyone?
Magnetic field. If you put magnetic field on the electric field.
Okay, well, you got a rough idea. Anyone else? Okay, so doesn't matter. I mean, we are going to discuss it anyways. So let's take a slab of material. Okay. And let's say I have these 2 terminals connected to my material, which I can send a current through. If you like, I can connect a battery as well. So this will be my voltage source. And basically I can measure voltage and current. These are parameters that I can measure. And there's another thing that I do. I connect, so this comes from the back. Okay. I connect a voltmeter to the sides of my sample. Okay? Then I apply a uniform magnetic field. Let me define this direction as the z direction, and this one as my y, and this one as my x direction. Well, let's swap them. Let's make this y, let's make this x. Okay? So, and this magnetic field is uniform throughout my sample. Now, what is the force if I take any electron under the influence of a magnetic field? What is the force that will act on that charged particle? Let's make it more general. Rather than an electron, let's talk about a charged particle. What is the force? So V cross B. V is the velocity of the particle. B is the magnetic field. Okay, and this cross product is basically you have two vectors. Let's say I have this vector v and this vector b. So when I take the cross product between them, I put my four fingers along the direction of my first vector, curl it towards the second vector. My thumb will show the resultant vector. So in this case, for instance, let's take that my electrons have a velocity in the x direction, okay, and my magnetic field points in the z direction. So curl this way. The force acting on an electron that's moving here will be towards that side because the electron carries a negative charge. So the force acting on a particle due to this magnetic field, I have velocity v, force will be in the minus y direction. Okay? So the magnitude of this guy will be what? Come on. Okay. Okay. So if there's an angle between them, the right hand rule will still apply, but the magnitude now will be slightly smaller, modified by sine theta. But if they're at 90 degrees, then the sine theta will be 1. You'll have the maximum magnitude. Okay, so that's the first thing, first force. That's, by the way, this is called the Lorentz force. With, if I add, so this is the magnetic field. But this is not the only force that's acting on my particle. I also have a potential difference across my sample. So there's an electric field within my sample. So that's straightforward. The charge of my particle times the electric field will give me the force acting on my charged particle. Now, can you see why we connected voltmeters to the sides of this sample? Under this magnetic field, the electrons will start deflecting to the edge of the sample. Okay? So I'll start collecting electrons here. And you can, for instance, for a semiconductor, you can take that holes will go the other way around. Okay? Or if you have a metal, you can imagine that you're leaving absence of electrons on the other side. So there are ion cores remaining behind. So what happens after I wait long enough? I have collected lots of electrons on the other side and lots of holes on that side. So there will be an electric field created within the material in minus y direction. And that electric field will also exert a force on my electrons and holes traveling through x direction. And it will reach an equilibrium when this electric force becomes, in terms of magnitude, becomes equal to the magnetic force applied on the particles. So I hooked up my battery, electrons are flowing, I turn on the magnetic field, I'll see that voltage rises to a point and then it will flat out because now my magnetic field cannot overcome the force that's created by the charges that are accumulated on the sides. So by basically measuring the potential difference on the sides, now I can measure certain quantities. And I'll show how this measurement will lead to the measurement of density of electrons.
Right now, so we have two electric fields?
Well, one is the one that we applied, we created. Two that formed because of the magnetic field.
So inside of
Yes.
the transfer,
Mhm.
we have right now two electric fields.
Exactly.
And the second one is equal to the magnetic field.
Force of the magnetic field. Magnitude of the force applied by the magnetic field. Okay? So if you look at a single electron that travels through this box, this is the magnetic field, this is its velocity. The force acting on this guy was into the board, but then the electric field that's created will pull on it. So I have two forces, two opposing forces that are equal in magnitude. So this electron, the new electron that enters into the system, will keep its velocity v. It cannot deviate to any direction. There will be a balance. Now, let's do a more rigorous treatment of what I just explained. And this is what happens when you look at this physically. But let's see how to calculate such things. Now, I have 3 minutes left, but rather than showing you how we derive, how we will end up getting density of electrons, perhaps I should prove you first how we can really study these objects that are supposed to be quantum mechanical, but how we can use semi-classical equations of motion. So I'm going to do a semi-classical approach. And the semi-classical approach is the basis of the diffusive electron transport. Okay? Which means electrons will have these diffusive characteristics. There will be scattering events and so on. So this is far from the mesoscopic regime. But it's a good idea to, I guess, show how the approach that I'm going to have is valid even for quantum mechanical objects. So we can write down this classical equation, which basically written in the phase space. So I'm looking at how each state moves in this k space, okay? So that's why everything that I write here is a function of k. And then this is basically del by del kx plus del by del ky, del by del k z, of course, they're in kx, ky. So this is basically a vector quantity, okay? And then dotted with the electric field that I can represent in the k space. Any questions? Well, okay. So I think just give me 1 more minute. So I can also write this down. So the time derivative of momentum, h bar k, is equal to this guy, plus, again, I'm going to confine myself to the phase space. Okay? So this is basically the manifestation of the same thing, but written in terms of a semi-classical way. Now, from here on, what I'm going to do is I'll define a distribution function okay? A function that shows under external forces, external influences, and scattering events, how my electrons are distributed within the K space. And this is not going to be identical to the Fermi-Dirac statistics, because Fermi-Dirac statistics applies for systems that are in equilibrium. Here I'm talking, I'm going to do the derivation for out of equilibrium systems. And I mean, it's not too straightforward in terms of derivation, but I think it's very useful to see why we have done all this transformation to the phase space and why we have insisted on basically using semi-classical equations of motion. It will become very clear that how we can apply quantum ideas to classical mechanics under certain approximations. We'll do it on Tuesday, though. Okay? Any questions?
The idea I got from Hall effect is that we avoided from the deflection of the electrons.
Well, we wanted deflection of electrons, and then it resulted in
At equilibrium,
yes.
no deflection.
Yeah. And by measuring voltage,
What did it do?
actually you will see when we finish this exercise of showing that semi-classical equations of motion actually can describe such a system, you will see that this voltage, which is called the Hall voltage, is a function, not a function, but it only depends on the density of electrons. So we'll show that. But you're right. The idea is apply magnetic field and wait till it reaches to equilibrium, which happens in a fraction of a fraction of a fraction of a millisecond. So as soon as you turn on, everything becomes into equilibrium. I mean, it happens in nanoseconds, actually, if you like. So, okay, any other questions? I'll try to set a midterm date sometime probably within the next few weeks. I'm trying to think of a format for the midterm. Again, I'd like to emphasize that the purpose of this course is not really, I mean, it's not an undergraduate course, so I really expect you to try to learn things from what we do here. So I don't want to push you too hard with midterms. So I can do a conceptual exam that will be conceptually challenging, but not too challenging in terms of calculations and so on. That's one way. It will be closed book, closed sources. I can do an open book, open laptop, open anything, but no discussion, but slightly more challenging questions, some equation solving as well. Or I can do a take-home midterm. So I haven't decided. I'll let you know when I decide and prepare questions. Okay. All right, so see you on Tuesday. Don't forget to send me your project topics.